Well, it's really a pleasure. When I got the invitation to come here and speak with you, I had to decide what it was I might speak about. And I looked for something that would make contact with this community, which I really admire a great deal. The kinds of things that you do and the way you've mattered in society and in industry has been really important. And I wanted to tell you a little bit about things that I have done where I thought, well, after I looked you up, I thought, well, maybe these guys could help. And so I'm kind of here on a recruiting mission. I'm kind of looking at some of the younger people. The older people, I'm sure you're wonderful. I'm kind of looking at the younger people. I'm here on a little bit of a recruiting mission because there's something I'd like to see happen. So I'm going to tell you the story of that and how I got to this point in my life. So about 25 years ago, I was lucky enough to become friendly with Abbas Al-Gamal, who he's more a solid-state circuits and systems guy, but maybe he's... Okay, great. So you take credit for him too. That's so good. That's great. And Abbas had just returned to Stanford from several years working in the Valley. And another friend, a mutual friend of ours, Joe Goodman, said, you know, look, this guy's really smart. You should go see what he wants to do now and hang out with him. And it was a great opportunity for me. And what Abbas did and what we did together was, it was just at the moment when the shift from CCD imagers into CMOS imagers was happening. And Abbas assembled a group of companies that would support our efforts to understand, well, what circuits should we be putting in these CMOS imagers, and how could we get the noise out, and what quality images would this be? And it was really kind of a confusing, interesting, exciting moment. And you know, I have many stories to tell, but basically the theme at that moment was, well, CCDs are great, CMOS imagers, they're kind of cute for a little peripheral thing, but never really going to happen. But sure, here's a little money, see if you can find some niche for it. And as you all know, it went much beyond that to this point where CMOS imagers are what you all have in your pockets now, and I'm sure many of you played a role in making that happen. Abbas had a particular idea that I was fond of, a digital pixel sensor where we actually had ADCs basically at every pixel that made the whole device digital, and that rolled out into a little company called Pixum. So my role in that was one, I'm a vision scientist. I'm somebody who thinks about how people see and how the brain works, and I'm somebody who's a perception person. And my role was, for one part, was to think about image quality. And when we got the data off the sensor, how could we render them to make nice-looking images so people would actually buy these parts? And the second thing was Abbas and his team were really experts in things like circuit design and SPICE, but not general programmers. And we took on the challenge, and by we, I mean myself and Ting Chen, who's now at Apple, and Peter Catrisa, and a number who's worked with Shan-Wei Fan at this point. We took on the question of, well, how could we simulate the properties of these devices in a way that we might speed the design of the circuits so that these imagers, we could go faster. We didn't have that much money, and we needed to do these tape outs and check them, but we wanted some help in the simulation bit. So we started working on simulation back in those days, and I became quite gripped by it, which I gather is a central theme here. And that ended up being a company that Joyce Farrell, who's here and who directs an affiliates program at Stanford now, we got involved in repurposing that software that got used by a number of companies involved in imaging up and down the valley, and we would always give it away to people in academia, some image systems engineering tools that really was centered around the question of designing these chips and so forth. So that brought me close to your community, right? I don't consider myself part of it, but you can see why I'm kind of interested in what you guys do, what all you folks do. And over the years since then, Abbas and I ended our project, our friendship continues, but that project, there comes a point where academics become kind of irrelevant to the way industry's rolling out. When they're selling 6 billion parts a year and you've got a little lab at Stanford, that's kind of adorable, but you don't really matter. And so we both moved on in different directions. But Joyce moved from HP Labs, where she had been, to Stanford around that time and started this affiliates program in which not just people building cameras, but people doing all kinds of imaging come by on a weekly basis and give talks. And there's a regular seminar series, and Bernd Giraud and Gordon Wetstein, two of our colleagues, picked up the pace and the breadth of the speaker series. Joyce organized a large number of symposia over the years of how things evolved from starting out with camera phones and standards, but moving into AR, VR. Most recently, she's taken us in the direction of medical imaging and artificial intelligence. And what I'm here to talk about today, given that's a little bit of personal history, is what I became envious of from watching the industry and seeing what it is these different parts of the community do. And the thing that is really striking to me now, and that's the main point of this presentation, is that you, in the form of various pieces of software that are sold downstairs here, and these other industries, the airplane manufacturers, circuit designs, other industries, even to some extent some parts of magnetic resonance imaging, where I do a lot of my work, have great simulators for your industry. You have things that are kind of consensus simulations, or things that you all believe are roughly true, though maybe not true down to every electron, but they give you guidance. They help you think about things. And we benefited so much from that when we did the CMOS, early CMOS imaging designs. And I really think that the imaging industry as a whole, and these are people who make cameras, displays, optics, sensors, that industry needs a consensus simulation environment so that it can speed development of different parts. And I would say, in a way, the most important thing that we learned from the years of consulting with all of these different companies who are each making their own different part and doing something is that even when you go into a company like, let's take IBM as an example, and you go to one group at IBM that might be working on the material science for a sensor, and they have to communicate to a different group at IBM that's worrying about the optics that'll be sitting in front of the sensor. Their ability to communicate between one another can be greatly enhanced by having a simulation software environment where they both communicate their measurements and methods into one unified framework. So the main message, and I'm going to give you two examples of that today in some detail so that you get a sense of what I think is involved in building such an environment and such a tool. The main message, however, is that I think that the imaging industry would really benefit from having a consensus tool where the calculations are validated, we trust one another when we build objects inside of that tool, and that having such a tool will really speed innovation and the development of a new generation of imaging devices. So now I'm going to tell you that story, exactly how that would work out. Okay, so I'm going to tell you two parts. I don't think it's possible in the modern age to give a talk without mentioning artificial intelligence and deep learning somewhere. And so the front one is loaded in particular for the design of imaging devices that can be used for the design of, so cameras for automotive applications and the design of such cameras, in particular for as inputs to artificial intelligence systems for locating other cars, pedestrians, and bicycles. And the second one will be a little more conventional, will be the use of these tools and how you would use an image system simulation environment to advance image quality measurements for the vast array of new devices, light field cameras, light field displays, head-mounted displays, augmented reality and virtual reality. It has real important applications there as well, and that'll be the two parts of the talk that I go through. Okay, so first, we're going to talk about the automotive applications and what goes into building a system there, and why I think it'd be good to have a consensus one that many people could build on top of. So the idea of how one designs cameras for automotive applications is you get some smart people in a room, OmniVision, Sony, places like this. They sit around, they say, you know, I think a sensor like this would be pretty good for your car. And they make some decision. Oh, there's a lot of red lights out there, so let's make a sensor that's got white pixels and red pixels, and maybe we can sell that. Okay. So, okay, well, how do we check that? Well, I don't know, let's go build it. Go build it. We'll put a color filter array on top of the sensor and stick it on a car, and then we'll have somebody drive it around. Okay. So now somebody's all of a sudden got a red and white, and these are for sale. You can go to OmniVision and buy them now. These are for sale. You've got these sensors sitting on cars, and somebody who's driven 500,000 miles to collect data. And they have to choose a particular lens, they have to choose a particular pixel size, they have to choose a particular set of color filters. There's a lot of particulars that go once you commit to actually building the thing. And then, God save us all, you've got to take the data and label it, because this is the age of machine learning and artificial intelligence, and nobody really wants to look at these images. You just want to know you don't want to run into another white truck. You don't want to stop at a stop sign. So now we've built the thing, we've driven it 500,000 miles, and we've labeled it. So now we see, okay, on an independent test set, because we all know about cross-validation and leave one out and all this kind of stuff, so on an independent data set that we've held out, we test it and we see how well it did, and we notice it did well on this, but didn't do so well on that, and we feed that back, and that's the design build loop. Well, that's really expensive, and that's really slow, and people just don't really do that. They do the forward part, but the feedback part, if you're interested in camera design, that's just not going to be a way that you go and you choose, oh, now I'm going to adjust the pixel size and do the whole thing again, or now I'm going to do it in some other way. So maybe what you do is you build a whole bunch of them up front, and you stick them all in the windshield of your car, drive them all around, and choose one of them, okay? And people, you see, people do this kind of stuff, but even so, how much room do you have on your windshield for how many cameras and so forth? So it's not a great approach. So you can see why somebody like me who's interested in the design of cameras for new applications like this would go and say, you know, gee, I kind of wish I could do this by simulation. If I could calculate up front, I might have some novel designs and turn up something interesting so that initial phase, when we're sitting around a room and thinking about what to do, we might be able to remove some of the really dumb ideas at least, and maybe try some ones that are a little riskier. So what's involved in that? Well, the first thing we needed data. And if we're going to do it in simulation, we need a way to simulate scenes. And these need to be appropriate scenes for the driving environment. And the good news, and to me this was not something I knew 5 years ago, but the folks in computer graphics split into a number of different camps. And some of them have, and I'm particularly thinking here of Matt Farr, who's the first author on this big book, who comes out of Pat Hanrahan's lab, developed open source tools that I think of, I label at least, quantitative computer graphics, in which scenes are built using physical principles of ray tracing that create very, very realistic and quantified values, so that we literally are tracing the scene radiance, the angles of rays on a wavelength basis and so forth that are physically accurate. And what I mean by that is that the ray tracing, those guys go backwards from the film plane or the sensor plane through the camera model, meaning through the optics. We've added a little bit for diffraction, because in some cases that matters, into the scene, They've got physical models of retroreflective materials, scattering properties of the light, participating media, and so forth. So with a little bit of effort, you get rather accurate models of what the scene radiance actually is in a driving scene. Usually at this point in the talk, somebody would say, if we were just sitting around schmoozing, somebody would say, well, but you know, those are kind of slow. Why don't you just use Unreal Engine or Unity or something like that, because they've got great driving simulations. And that's the point at which I say, look, those pieces of software are great. We call those rasterization methods in computer graphics. And it is true that they do really nice renderings of cars and so forth, but they're not physically accurate. And if you're driving, and if you're designing a camera, you actually need to know the radiance and the directions of the rays, and you need to know it on a wavelength basis. And that actually shows when you do the rendering of similar objects, the quality of the images produced by companies such as Pixar or in these ray tracing calculations is more realistic than the quality that you see in these Grand Theft Auto kinds of applications, which are cool and compelling and nothing against them. But the realism of the ray tracing, although it's slow, is worth it to a camera designer like me. And that's another place where there might be some overlap with some of you, and I'll say something about that later. Okay, so we can, so what's involved? Okay, so I showed you a picture of a car in some context, but remember that to build simulations of scenes for complex driving applications, we need to have the mesh of the car, we need to have it labeled, what part's the window, where's the car paint, headlights, so forth, all these things. We need to be able to control the appearance by having different models of the way it is, the paint reflects, the metal reflects, and so forth. That lets us change many things. It's kind of easy, the glass, the leather inside, and so forth. And so that's how we spent a couple of years at this point, just learning what it is we didn't know how to do to make really realistic looking models. And I would say that given that one of us has learned, there's no need for everybody else to learn. We give this stuff away, we'd be happy for other people to validate it, extend it in some way. And it's not kind of fundamental research at this point. It was just a question of prying it out of the minds of the folks in computer graphics who already knew how to do this. And we now have systems set up that we're very happy to share with anybody. Now, that's one car I've shown you. But driving scenes aren't one car. Driving scenes, I mean, one of the things I've learned about the world is how complicated it is from trying to assemble scenes. Just, look around you. Look at all the plates, the tables, the chairs, the people. Well, car scenes are complicated also. And to generate car scenes, you need models of streets and cars and trees and pedestrians and bicyclists and road signs and so forth. And again, fortunately, there's a whole industry out there, people who study vehicular flow, and one of the things that we stumbled across was something called simulation of urban mobility, SUMO. And this is a driving simulator where you can set parameters, and they've worked hard to match the statistics of these driving simulators, and you see it driving up there to the left, so that you can sample the outputs of that and place your cars and pedestrians and so forth inside of on highways or on streets and so forth. And similarly, you can place buildings in that context. So we need a place to store all these things. So we need a nice database environment where we can put all these assets and randomly pull them out and reassemble them into scenes. And so we did that. And then we need, and this was home base for us, we need models of the sensors and the optics that are going to be placed in these scenes and look at the cars and trees and so forth. And then finally, and this is something that the machine learning community has done really well, we need models such as these convolutional neural networks And I gather, ResNet is quite popular now, but whatever is next, and PyTorch or TensorFlow, they seem to be competing with one another every few months. We need ways to incorporate those into this also. And so what I've shown you is that there's just a collection of things that we needed to pull together, and that are a little tricky, and I'm going to summarize them here, to go and build simulated scenes like this one. So this is an example of all these buildings don't exist, the trees don't exist. You can see Vista Lab is the name of our lab, 2018. All these guys from Berkeley are winning prizes, but I got the Stanford logo up here on the license plate. And we've got rather complicated scenes, and we need to be able to make tens of thousands or hundreds of thousands of these scenes for the training and machine learning applications. And so that's simulated. Everything is computed because it's quantitative computer graphics on a spectral basis, and I need that so I can go through the lenses and know what to do when I arrive at my red or white color filters. Everything's spectral. I can simulate my sensor. This is a conventional Bayer pattern, but I can put in a red-white sensor if I want to check whether the guys in OmniVision had a good idea. I can put this sensor in and rerun my tests on that and so forth. And or a mix between put in a white pixel along with the red, green, and blue. And because it's simulation, the labeling, and this is huge, obviously, the labeling comes for free. It's simulation. So I know what everything was. I know the distance to every point. We're adding LiDAR simulation into this environment as we speak. And so that's basically where we stood on that. And so just to remind you, we started out with assets. We put them in a database. We had ways of generating scenes from the data in the database. We had ways of simulating the sensor and putting it in as parts so we could experiment with different types of sensors. And then we have the whole infrastructure provided kindly by the machine learning community through either TensorFlow or PyTorch, or we tend to be using PyTorch, even though this says TensorFlow at this moment, to complete the loop. So the point then here is it was a really fun experience for us to assemble this and to start testing ideas. I won't, I'm happy to take you through what it is we think we're learning. But really the first point that I told you was I think the imaging industry generally could benefit from validated environment like this, image systems simulation environment. And the second point is that an environment like this, when I'm thinking myself as a young professor or somebody who has a skill in optics or somewhere that isn't right in the sweet spot of all this, and you want them involved, you want what they know as part of your project. Being able to hand them an environment like this has real value, because most people don't want to, it's not fun for them to assemble all the different parts. You just want them to be able to work in an environment like this where they can contribute what they can to the general good. And so even commercial startups, for example, I think would benefit from being able to have this. And the other phrase that I really want to emphasize is that if this was just my lab who did this, and I went around and tried to bully you into using it because, I don't know, I'm old or something, and so I could stare you down. So it wouldn't work very well. It really has to be something that we all trust, and that people from different places believe and buy into and believe that the calculation is right. You see that, for example, in the optics community. Everybody seems to trust ZMAX. I know that you folks have a set of positive experiences with some of your software. I better not name anything here, but because somebody will rise up an objection. But you use SPICE, you use other kinds of code that is helpful. And I think that without that consensus, it's a problem. So let me just close this section of the talk. So that's my next point. I think building such an environment, getting support for building that environment collaboration between academia and industry would be really valuable. Let me say, as an example, just one simulation, and Zhenyi Liu, who's been working with me on this, and Henrik Blazinski is now at Apple, and Zhenyi is a student still working with me in the lab. We've been doing simulations, for example, what's the impact of pixel size on these kinds of things? And what's shown here is just an example of one simulation where we have many scenes, cars are at different distances in those scenes, and if we take a small pixel size, so that you have a lot of spatial resolution, what's the precision of detecting a car as a function of distance? And you can see that it really can see when it's a good optics and a fine pixel size, you can see out to 200 meters, and everything is really quite, it's got units. If you go coarser, down to 6 micron pixels, which are on the market as well, and even with optimized optics, you fall off and you're only good to about 50 to 70 meters. So you get insights about what's likely to work, what the difference will be between as a function of pixel size and so forth from these simulations that can be quite, that I believe are valuable. And the summary for this section is that a purely empirical approach to camera design, build them, hang them on your windshield, drive around a lot, label them, and so forth, really isn't practical if you care about innovation in cameras. If you're just happy to choose one of the existing cameras, this is not for you. But if you're somebody like me who likes designing new arrays of cameras with different types of pixels and color filter arrays and light field options and so forth, you really need to go simulation. And we built one, and we'd be thrilled to have colleagues who want to build on that or extend it or improve it in some way. I say this usually when I'm at an automotive conference rather than here, but just to make the point and then move on. The car industry, turns out they make a lot of cars. Turns out they're going to buy a lot of camera sensors. They're going to sell a lot of systems that you guys are designing and building and thinking about, and that's going to drive demand. And my observation about the sensor industry is that if you tell them what you want, they can do a lot of stuff. They can really, if you know what you want, they do stuff. And that really played out in the cell phone case, and I think it'll play out here. The automotive folks don't yet know what they want. They really are taking what's on the shelf and saying, I don't know, let's just use any old camera, it's all the same, or I don't care what camera I'm using. I don't think that'll last. So I'm thinking that these simulations can be particularly helpful in setting standards for how it is we reduce the number of traffic fatalities, how it is we have an impact on that world. Okay, that's the end of the first part. And now I'm going to take us into something related. You'll see the parallels, but it's different. And, but yet it still calls out for an image system simulation environment. And this is a case of display design and perceptual image quality. So, by the way, I should say that this work, that first work largely came out of my lab with Zhenyi and Henrik. This work is collaborative with a number of people, including Joyce Farrell, who's sitting here, but Dave Brainerd, who's at the University of Pennsylvania, and Nicholas Kataris have played a really critical role in collaborating with them on this. And the first part, I should add, I want to thank the folks from Olympus and Samsung who have helped support that work. And this part, the folks at Facebook and Oculus have been particularly helpful. And the folks from Huawei have been helpful throughout. And that's another conversation. We can discuss the whole Huawei thing later. And this is, I should emphasize, these are all just gifts from Huawei and open source code. And not feeling threatened by any of that. So thank you to our colleagues at Huawei. Okay, so second part. The imaging industry on this side, cameras and displays, just also, you may think that because they're selling 6 billion cell phone cameras, that they're kind of locked in and nothing changes. But boy, that's not true. It's just really active. And people are building based on the money that they made, they're building all kinds of new displays, and here are just an array of cameras. By the way, I'll take all these slides. I always turn them into PDFs and post them on my website. You're welcome to have them all. They'll just, all of my slides from the last 10 years or so are up on my website. And the displays in particular I'm interested in because a young colleague, Gordon Wetstein, got us particularly interested in these light field displays and these kinds of technologies. And head-mounted displays, and Joyce organized all these speakers in the early days from the AR, mixed reality, virtual reality, one kind of reality, anything but reality is good. And so they're doing all kinds of stuff. And they too need means for simulating in advance what's going to happen when I build this kind of a display or this kind of a camera. And they're particularly interested, they're selling to you. They want you to go and buy one of these displays or one of these cameras, and they want it to look good to you. So home base for me is the visual system, the human visual system. And I am therefore interested in perceptual image quality metrics. And you know, and when I teach in engineering, it actually can be a little bit frustrating for me. I'm mentioning this to Subhasish in particular. But you know, you go over to the School of Engineering, and they have lots of image quality metrics that they use all the time. They're all kind of structured like this. You go, I teach a course over there, and so I get the feedback a lot. And the idea is this: you have a display, and well, how did you drive that display? Well, you had RGB values that you put in the frame buffer, and that puts something up on the display. Now, maybe you've got RGB values from, you know what the perfect ones are because, I don't know, because you're an engineer and you know what perfection is. And then you say, but then I actually had some delivered to me from that camera that was imperfect, or something delivered through a compression algorithm, or delivered in some other way that is not perfect. And I'd like to compare the two. And so what do? Well, what I do, by and large, is I put them, I take those RGB values, basically this is an input referred assessment, and I compare the ideal RGB values with the ones that are delivered to me from my compression algorithm after it was done. So I'm comparing in an input referred way, which seems plausible at the time, and the really big algorithms like structural similarities, SSIM, which has been, the paper's been cited more than 20,000 times. They've won an Academy and an Emmy, television Emmy, for having developed this, or PSNR, or multi-scale SSIM. These all work this way on the input to the display device. Well, if you only have one display device, just an RGB display, and they're all calibrated to be kind of the same, that's not a terrible idea. But if you're trying to build new devices, it's really quite limiting. So new devices look like this, like a HoloLens fantasy, where you've got some photons coming to your eye from the environment, some photons are delivered by the device itself, or you're doing medical education training. We had a great, at Joyce's conference, we had Mark Griswold from Case Western show his system for virtual reality for medical training, is illustrated here. And we had the folks from Oculus and Berkeley, and we're quite friendly with them normally, have multifocal displays where there isn't a single RGB. Every plane in the display device for different focal lengths has its own separate image that's constructed in some way. Well, there isn't an RGB, single RGB, so you can't use these other metrics. So the alternative idea is, instead of comparing out there at the input referred space, there's another approach that also exists and that we're advocating for here, is to make the comparison at the other bottleneck in the system. After the photons go through the optics of the eye and arrive at the eye, that's another bottleneck. That's another place where you can make a comparison. So I've shifted from comparing on the input side to now comparing here at the back of the eye. And that seems to us like, for the future, a critical move to make. But to do that, you need to be able to simulate how that device is going to produce an array of photons that can pass through the optics of the eye, and then what impact will that have on the human photoreceptors at the back of the eye, and then you need to have metrics for comparing those things. And so that's the fourth idea in this presentation, is that image system simulation of the human eye can really be used as a basis for a next generation of image quality metrics for the design of these advanced displays. That's the idea. And the camera rigs that are needed to gather the information for those. So I'm going to show you what that looks like now with just a few more slides before we end, to give you a sense that the human side, because I know not many of you have taken psychology classes in the last decade, and I just want you to remember how important, and it might not be known to you even, but the properties of the human eye are very important for the design of these devices. So for example, even the human visual system is extremely active and influential in how the quality of what you see. You can all see, for example, the white chess pieces here, and you can also see the black chess pieces. And because I'm a psychologist, maybe you won't be surprised to know that this white king here and this black king here are exactly the same. Physically, if you measure the photons coming to you, they're exactly the same. And I'll show that to you by just dropping down the white one and slipping it into the place of the black one. See, they're exactly the same. So your visual system is doing a lot of stuff to analyze. So when I tell you that I'd like you to have your metrics based on not the RGB input to the display, but what actually arrives and is captured by your visual system, that's not a trivial move. That's a move where I'm going to be accounting for a lot of factors that have to do with visual perception. To read a little bit more about that, I at some point wrote a textbook that I'll be updating on the foundations of vision. And if you're interested in vision science, bless your heart, we need more customers. So the steps in doing a simulation like this are really overlapping with everything I told you about the automotive application. We need to be able to simulate the scenes, which in this case has to do with the displays, and when they're mixed reality, they're actually the environment as well as the overlays that are projected onto the environment that reach your retina. We need to be able to simulate the optics of your eye, the way the photons are captured and transduced into electrical signals by the back of the eye. I'm happy to stop here and retire. That'll be okay with me. Some of the younger people will be going further in their careers and going through the retinal transduction process and processing itself. And of course, at the end, to make a judgment, we need an inference, and we need a brain there somewhere. So, and we've made some progress on this, but this is another project that's in process, and I particularly want to mention Tricia Liane is finishing her dissertation on this topic, and has a series of papers in process about this. She started to put them up on bioRxiv. And so for one thing is there's 100 years of history of people building models of the optics of the eye. And something you should know is that not all those optics models are in great agreement, but they're not in terrible agreement. And this is a picture of 3 famous models and what these 3 serious groups said about how a particular image with the A, B, and C at different distances from the person looking at it, how they would be rendered at the back of the eye, the retinal irradiance. So we need to know more about that. We need to know stuff. One of the features of your eye is that it's in constant motion. And when you're looking at things, if your eye doesn't move, if things are fixed on your eye, they actually fade from your vision. So motion is an important part of this system that isn't exactly the same when you take pictures of things for say, automotive applications. So the statistical nature of eye movements and eye movement patterns is important for us to account for. You might see here I've colored the receptors at the back of the eye as red, green, and blue, and they're quite inhomogeneous at the back of your eye. In the very, very center, you have very high density, very small receptors, and they change size quite a bit as you go from the center to the periphery. And so we need to account for that. We need to be able to account for distances and just the way things move around at scale. We need to account for the inert pigments that are present in your lens. There's a pigment called a macular pigment that sits on the front of your retina. And people who smoke, the macular pigment is wiped away. People who don't smoke still have it. It has a massive impact on what a different person will see, what light will actually arrive at their photoreceptors. The other thing is most of you, not all of us, but mostly all of us actually don't carry one eye, but we have two eyes. And we combine the two eyes. So these simulations are important. And for head-mounted displays, the fact that you have two eyes is extremely important. And so these simulations can help us with that. One of the key aspects of that industry has been that the fact that the displays are in fact a fixed distance, but in normal vision, when you look at something far away or something close, your eyes verge towards one another when it's close and are more parallel when it's far away. And this is just simulation showing that you can simulate what comes to the two eyes as a function of distance and deal with that as part of these metrics as well. And that depending on the light level, your pupil opens to different amounts. And as your pupil changes from being small, where the distance is sharp, where the things at distance are sharp, to large, where things at distance are blurred, that's another important visual cue. So all of these things are, same part of this image system simulation. They too are a little bit hard to get right. So, we're kind of proud of the fact that we worked on these things and managed to get them right and so forth. But once it's done once, I would prefer that somebody else check our work and find the errors in it and then build on it instead of just saying, the heck with those guys at Stanford. They did it. We're just going to do it again. What the heck? So I'd love to see these things checked, consensus build up, validate, give people a platform so that these fundamental things that I didn't invent, but that we have implemented, get built upon and get used in future way. And to support that, I wish we were better at this, but we're doing the best we can to write documentation. Imagine how thrilling it is to wake up in the morning and say, what am I doing today? Well, I'm going to be documenting this stuff. And it's really, really important, and we need help on that, and I'm doing the best I can, and I'm always talking to students about that. Everything is open source. The ideas, some of them are new, but most of them are fundamental physics, optics, data management, how do you run things in the cloud, things of this sort. We use Docker containers a lot for scale to go faster. We use Kubernetes to manage things. Stuff like that. So we're doing the best we can to build a platform that we hope other people could join in on, and we're building resources for that. And so my last point of the lecture is just to say that to roll this thing out, I've been fortunate to be involved in some commercial enterprises myself, and that I understand that to roll this thing out of an academic lab into a place where somebody at Samsung, who've been supportive, or IBM, or Facebook, could actually use this, will require additional looks at it by people who are really deep in computer science technologies to make sure that it works well and scales well and makes sense. And incorporating those methods to turn this into an industrial tool rather than something that runs in the Wandel lab will require work. And I hope that someone will be interested in helping. I opened up by saying I was here to recruit people. So there you go. There's my recruitment pitch. I'd like us to find some folks who'd like to build a consensus validated platform that might be beneficial as a software tool for the imaging industry. And I really want to thank all the folks on these slides here. Zhen Yi, who came from 2 years, has been in the lab in China, is headed back in a couple of months, has been great. Henrik really did a lot of stuff to get us going. Tricia has been a fantastic student. Joyce has been just helpful in 1,000 ways in envisioning this. Dave Brainerd, Nicholas Kataris have been just great collaborators. It's been a kind of a small but focused group on building these things out. And we're looking for friends. Thank you very much for your attention.
Brian, for the very interesting talk. So, questions from the audience? Yes.
For the first part, first of all, fascinating presentation. You know, I don't think I would fly to Las Vegas to hear this. But for the first part, can you give us a sense for how fast the simulations are, from end to end, from synthesizing and doing all the way to,
Yeah, sure. I'm glad to do that. So I'll tell you what the slow parts are, because the fast parts are fast enough I don't know. The way we make any single image for the ray trace at high enough quality so that the noise, so there's rendering noise in the ray trace process, you need to send out enough rays to get rid of the noise. And that takes about half an hour for a single image. And what we do, so that will change, but not based on anything we do, but based on stuff that Matt Farr is doing at NVIDIA. So that community they're excited about an AI way to reduce noise. But we don't really care, even in my lab, and I'll tell you why. Because we use cloud scaling to go fire up, everything is Dockerized. So we fire up a few hundred to a few thousand Docker images, and even to get 1,000 takes us 2 hours because it's a little slow to control the processes rather than 1 hour or 20 minutes or something like that. So the main issue is the money, not the speed. And we've been fortunate. It's not that much money. I mean, by the standards of this community, it's not that much money to pay Google bill. So, and then the rest is actually more, I'm not smart enough to go faster. So the hardest part, the slowest part is the ray tracing. Taking the images and turning them into a sensor image is seconds. Yeah.
Any other questions from the audience? Yes.
So you made a big point of saying to not build your own simulation stuff if they already exist. Before you built these tools, were there existing simulations?
Yeah, thanks. Yeah, am I as good as I'm telling you to be? That's very fair. I don't know. I try. I'm pretty confident that on the image systems engineering toolbox, just the sensor side, we had been around that. And I kind of knew that industry, and I think we were, people would tell me, oh yeah, I've got that in my lab, but I can't really share it with you because, I work for company XYZ, and I can't really give that to you, but what you're doing is good. So we had the only open source one that I could actually get my hands on. Notice I didn't build PBRT. That was another open source tool. I just took it. And then actually they teach classes on it, and the students started adding modules to it. And there's an open PBRT community. So we built that. I didn't build ResNet and the CNN that we use. So we're just using that. We could use others as well, but we picked that one, and we used FastR CNN first and then ResNet. What are the other parts? The database management part, honest to God, I wish there were things. I should have disclosed this. I started Flywheel. It's a company that does data management for magnetic resonance imaging. So I just took that. So yeah, I guess I've done nothing but steal and beg, and I'd be happy to steal and beg other better parts too. Yeah, I'd say the only part we really wrote was the ISET part. Oh yeah, 500. Okay, they used it too.
Any other questions? Otherwise, I have one interesting. So you mentioned that there is the part of understanding better how the eye works, ready to go there. But if I go a little bit a step further, every single eye is very different. So we don't see exactly the same thing. I have been actually working a little bit with neuroscience, and that's what I understood, that something that you see well, the other one, camera doesn't seem the same. So how would you actually personalize the camera? So once you understand how the eye works, how would you personalize it?
I love that. I love that question. I'm going to restate it, but that's great. There's always a tension in human factors there's the average person, and then there are actual people. And your point is that the optics of every eye, I'm 68, and my eyes have their own characteristic. I wear reading glasses and so forth. And the way you characterize somebody's eye like mine in the modern age thoroughly is use these methods called adaptive optics to go and get basically the space varying point spread function. And the software has, as one of its tools, as that example, as one of its tools, the ability to run the whole distribution. In fact, maybe you know Pablo Artal,
Yes.
who's a fantastic adaptive optics scientist. He ships us data from people of different ages and different visual field heights so that we can rerun these simulations to make sure that, some people just want to know the average, and some people want to know the 95th percentile, the most blurry versus the sharpest and so forth. And so, the software has at its core the ability to insert adaptive optics characterizations of the lens. Variations, another case is color blindness. So we can change the photopigments, and people who are missing a photopigment, we can run that version of the simulation. There are people who have slightly shifted photopigments, we can run that simulation. So because it's open source and we can change it, we can look at the distribution of individuals and try to get 99% of them, or just go for the mean, and that's a choice that the designer would use, and that's comes with the territory. So I really appreciate your point, and that's something we worry about a lot.
Okay, any other questions? Yes, Miguel.
One of the things that you mentioned when you do the creation of the images, you do away with the labeling. And it sounded to me like you were saying that from the point of view, that's a lot of effort that I avoid. But I'm wondering if from the point of view of correctness, that's also an issue. You actually get much better correction in the labeling.
Oh, so nice of you to say. I'll repeat your comment, really. You posed it as a question, but the question is, because we're in simulation, we don't make any errors in our labels beyond programming errors. But have I ever looked at a data set from, I don't know, some competing university somewhere, and did they ever have any errors in their labels? Amazingly enough, there are errors. There are errors in the labels, and I'm going to pick on Baidu here because they're big and they don't care if I pick on them. But Baidu has wonderfully distributed an enormous data set, and the students can find errors. You go through 25 images and you'll find 1-2% of the labels will be incorrect. It's probably not enough to matter, and they did a good job, but it's hard to get those labels right, and the simulation helps with that.
Okay, so once again, I would like to thank very much Brian for all the work and so on. So since I know he doesn't like to receive very often awards, prizes, and this type of things, it's hidden here. So we have something for you. That we always do. So this is actually a plaque that we always give to our distinguished lecturers to really show you that we really thank you very much for all your contribution to DAC and CIDA. And we really hope that we can count on you in the future as well.
Thank you.
Okay, so this concludes our CIDA luncheon. So see you next year, and we hope you enjoy DAC very much. As they have already announced, DAC will be back in San Francisco next year. Thank you very much for
Thank you.
Very interesting.
Good, thank you.
Yeah, we do a lot of things now with drones, but it's a different thing that we work on. It's an image visual system. We actually do event-driven cameras and so on. This is something that we actually do a lot in my house.
I've always had students wanting to work on it. We never did simulations or event-driven cameras, but the students have always been